So our last speaker for this session is Hitesh. So he's going to talk about bridging induced coil-to-globule transitions in polymers.
First of all, I would like to thank the organizer to giving me the opportunity to present my work here. So the title of my talk will be Bridging Induced Coil-to-Globule Transition in Polymers. So after experimental and more technical talks, let's end the day with the more fundamental question, how many ways coil-to-globule transition can happen. So we all know now what polymer is. A polymer is a large molecule made up of repeating units called monomers, and these monomers are connected to each other through a covalent bond to form long chains. And there are various examples in our day-to-day life of polymers, in synthetic as well as biological. So I'm more interested into the conformation of a polymer chain, how a polymer chain can take different conformation. So before that, what polymer conformation will be there in different solvent quality, is known that in good solvent condition, chain will be in the extended kind of form. What we call a good solvent condition is when the attraction between the monomer is less than the monomer-Crowther interaction, solvent attraction. We'll call that as a good solvent condition, that and the chain will be in the extended form by the logic that the monomer wants to have more contact with the solvent. And on the other hand, the poor solvent condition will be the condition when the monomer attraction is high than the monomer solvent attraction, and the chain don't want to in contact with the solvent, and hence form a collapse kind of form that we also call globule, and extended kind of form is known as coil kind of structure. And these in good solvent and poor solvent, these Rg, radius of gyration, follows a nice scaling behavior. Rg varies as n to the power 3 by 5, and within poor solvent, Rg varies n to the power 1 by 3, where n is the number of monomer in a single chain, and these 3 by 5 and 1 by 3 is valid in 3D. It's a dimensional dependence coefficient. And in general, R varies as n to the power nu. Nu is scaling exponent that can be used to find the regime in which polymer is in. It can be in good, theta, or poor solvent. Then, what are the common ways in which we can get a coil-to-globule transition? And the coil-to-globule transition is kind of relevant, as some of the speakers already told that they are biologically relevant forms, whether the chain is in the extended kind or the coil kind of structure or in the globule kind of structure. So we know that, as I explained, the solvent condition can play a role in achieving the coil-to-globule transition. If the solvent quality is good and we module it to a poor solvent condition, we'll get a extended to collapse kind of structure. Then there are core non-solvency is one of the another way we can get coil-to-globule transition, where if a single polymer chain is miscible or in good solvent condition for type 1 solvent and individually for type 2 as well, the mixture of type 1 and type 2 can give rise to a poor solvent condition and will make the chain collapse. This phenomena is known as co-non-solvency, and then the same can be achieved through temperature mediated. Increasing the temperature or decreasing the temperature can also induce the coil to globule or globule to coil as well, depending on whether the chain display LCST or UCSEST, lower critical solution temperature or upper critical solution temperature. Same if we have a charged polymer, that can also showcase coil to globule transition if we mainly increase the charge density on the each monomer or the backbone charge density. Polymer doesn't found themselves in a single solvent condition. They generally found themselves in a very crowded environment. In a biological context, in a particular nucleus can have a various segment, which we can call them a Crowder. Crowder is a very basic term we can use. It can be of different shapes, sizes, as well as can be macromolecule. So Crowder is very generic term, and so it's really important to study polymer chain in a crowded environment, right? So if we have a Crowder in our system, they can have typically two types of interaction with the polymer chain. First is they can have a repulsive interaction with the polymer chain, and that gives rise to what known as depletion kind of effect, where when these Crowder density is increased and above a threshold value of the density, we'll see a coil to globule kind of transition, and these kind of Crowder depleted from the surface of the polymer chain to gain translational entropy, and this phenomenon is known as depletion effect. So here are the you can see as the density is increased, they kind of depleted from the surface to make the chain collapse, right? So the other interaction a Crowder can have with the polymer chain or monomer is attraction. Typically, one would think that if the Crowder have an attraction with the monomers, chain would like to be into the extended form, as the same logic I gave for the good solvent condition, that they want to be in the more contact with the Crowder particle. But what it has been found that the chain collapses with the increasing the attraction between the polymer and the solvent particle or the Crowder particle. The attraction, this attractive Crowder shows some counterintuitive behavior. So what happening? So you can see here the chain is was extended for less attraction, but as the attraction is increased, the chain is now forming a globule kind of structure. And what happened? The Crowder particle is acting as a bridge or a glue between the distant monomer to induce the collapse behavior. So what is happening? The single Crowder particle, the green one is showing here, is now kind of acting as a bridge or a glue between the distant monomer. You can see here. So single can act as a kind of bridge between the two distant monomer. So there are a few studies here to showcase this, that indeed as we increase the polymer and the solvent attraction or the polymer or the Crowder attraction, we see the chain is going from collapse to extended to collapse kind of behavior. For these are some of the studies. So hence there is another way of this C to G transition is through adaptive Crowder, and we are calling that a bridging interaction. So what questions are we addressing? So the earlier studies I have shown is kind of not complete in the sense they have focused on a very restricted range of parameters. For example, some of the studies only restricted to a particular monomer attraction, or some to particular densities, and some particular like short chains and all. And also there was no report of collapse to collapse transition as well in the literature, and this collapse to collapse transition has not been conclusive thus far. And apart from these questions, we are also trying to find out the critical value of the attraction between the monomer and the Crowder, which give rise to the this transition. So we are constructing a phase diagram for the critical value of the transitions. So before the results, I will show what model we use. So it's a very basic model we can use. So it's a bead spring model with a single chain surrounded by the Crowder particles. In the blue you can see, and the solvent we have taken as implicit, that the monomer interaction will tell us whether the solvent condition is good or bad. And every non-bonded particle interacts via edge interaction given by this mathematical form, and every bonded like adjacent bonded particle is modeled by the harmonic bond by the classical Hooke's law. Then the phase diagram. So this was one of our aim. So we analyze for different interaction of the monomer attraction and the monomer Crowder attraction. We analyze the radius of gyration of the chain, and I'll explain the radius of gyration behavior with the different interactions. So if we take epsilon mm.1, that means weakly attractive monomer, that the chain was in the extended form when there is no Crowder around. So if you see here, if there is no Crowder, the red curve shows us that the chain is in the extended form. And as we increase epsilon mm, that means we are increasing the monomer attraction, that now the chain is going to good to poor kind of condition, and now the chain is going from extended to collapse kind of behavior, right? So it was obvious. But as we look at this red curve and we increase the epsilon mc, that means increasing the monomer Crowder attraction, we see that there is a nice decrease in the radius of gyration, and chain is going from a extended kind of structure to globule kind of structure, right? So from there we find the inflection point of each curve to find the critical value where this transition occur, and from there we made a phase diagram out of it. And this looks like something this. So we primarily determine three phases. First is extended phase, that this one due to weak intrapolymer attraction, and then as we go increase the epsilon mm, we see that we go to another phase, CI phase, that is collapse phase due to the intrapolymer interaction. Here the Crowder is playing no role; it's totally governed by the monomer attraction. But one more phase we have found. We found another collapse phase, that is collapse phase due to the bridging interaction, and this occur for both in CI to CB phase as well as extended to CB phase, right? So there are some this is the E phase I'm showing. That's in the presence of Crowder. It shows most extended. Here the CI phase, you can see where there are very less number of Crowder which are around it, and in CB phase you can see there are the collapse phase, and it's mostly the Crowders are playing part in making this transition happen, right? So even though both the collapse phases are same, we are saying that they are two different phases we are determining, CI and CB, because they are maybe collapsible, but they're structurally quite different. You can see from here, the black and the red curve shows that this is CI phase, totally determined by the monomer-monomer attraction. We see there are no Crowder inside this. So this y-axis is density profile of the Crowders. So we can see the black curve is showing 0 up to a certain distance, and then becomes equal to the bulk density, showing there is no Crowder inside the globule. Where in the CB phase, we can see there are quite a huge number of Crowder which are sitting inside the globule, right? So they are quite, and from same can be interpreted from the G of R plot. We can see in the CI phase, the radial distribution function for monomer, we see a peak, first peak. That means there is a neighbor of a particular monomer is a neighbor. But the same peak is absent for the CB phase, GMM, you can see the blue curve, there is no first peak. That means, and in the GMC, that monomer Crowder radial distribution function, we see the peak is emerged where the peak is absent for GMM in the CB phase. That means now the monomer particle is kind of replaced by the Crowder particle inside the globule. So these the point is that these two collapse phases are quite different structurally. Then what is the effect of density? We look. So some of the earlier studies showed that there is from the collapse to collapse transition is directly happening. We also see in our case that this one, initially we work with this particular density very dilute system, and we see that the red curve is going from one collapse CI phase to CB phase directly without any extended kind of structure. But some of the earlier studies as well, and our study shows that as we increase the density, we will see a intermediate extended phase as well. So it's not going directly to CI to CB phase. There is an intermediate extended phase as well. So we can conclude here in the sense that these transition like CI to CB or E to CB all are density dependent, strictly density dependent. They are not absolute transitions. Then naturally we ask again same question: what happens if the polymer is charged 1? Till now I have talked about the neutral polymer. What happens if the polymer is charged 1? We give charge to each monomer. So charged polymer has various examples in our day-to-day life as biological polymer as well as synthetic polymer. So in model will change in the sense that we now put charges on each of the monomer with some negative charge, and then to neutralize the system we have counter ions of the different valencies z equal to 1, 2, 3, and again the other things are same, and non-bonded particle will interact via Aj potential, and the charged one will interact via electrostatic potential, and the bonded will be again the same harmonic potential, right? So before putting Crowder in a charge system, what we know about charge system without Crowders? We have a polar-electrolyte chain and just counter ions around it. What we know about that? How that transition happen? So we know that it's been established now that a poly-electrolyte is the name of charged polymer, undergoes a coil-to-globule transition as the charge density on the chain backbone is increased above a threshold, right? So that means if we have charges on chain backbone, and if we modulate the charges on each monomer, there is a particular value AC of the charge density above which the chain will go from extended to collapse kind of structure, right? So there are few studies which are these are the studies which shows what is the value of AC to find for the different. So this AC value will depend on the valency of the counter ion as well, and the various other parameters. So and this kind of collapse can be understood by the phenomena called Manning condensation. And what happens that the counter ions come and condense on the chain backbone to neutralize the system and make the chain collapse. There are few studies more recently going on with the dipole-dipole interaction and all, where people are trying to understand what is the exact force which is governing this extended to collapse kind of transition as we increase the chain backbone density, right? Now, if we put Crowder inside that, and we have two regimes now, A less than AC and A is greater than AC. A less than AC means when chain was in extended kind of regime, when there was no Crowder, right? So if we put Crowders and increase the attraction between the monomer and the Crowder, what we see is a nice, again, chain extended to collapse kind of behavior. And for two different balances I'm showing here, Z equal to 1 and Z equal to 3, for both of them, chain was in the extended form. You can see from the RG values here, when the value of A was less than AC, and all of them are going to extended to collapse kind of behavior. And we can see this is for highest value of epsilon MC, that the highest value of monomer Crowder attraction. We see that the Crowder inside the globule, this is again the density profile of the Crowder and monomer. We can see the Crowder are more than monomers inside the globule at the profile. And hence we are showing that the collapse phase is consists of Crowder particle instead of counter ions. So this is totally governed by the Crowders, right? Then the other regime, we have A greater than AC, where chain was already in the collapse form. Then there were no Crowders because of the Manning condensation and the thing. So we can see the value of RG is in the collapse regime when for all these A by AC value we have taken. And we can see that again the chain goes from collapse to collapse conformation, but now both of the collapse form are again structurally different in the sense we can see the Crowder numbers are inside the globule is quite different for the two states. You can see 4.1, that is the CEI phase. There are no Crowder inside, but in the CB phase we have now the Crowder inside. And to construct a phase diagram, that RG doesn't seems to be a good parameter, so we made a plot rho bar C. That means number of Crowder particle inside within the RG of the center of mass, and that varies nicely with epsilon MC. And we again find the inflation point for different values of A by AC to construct a phase diagram. And this is our phase diagram looks like. For the charge one, we can see for Z equal to 3, it looks similar to what we got for the neutral one. And there are three phases we are again explaining the same way. E is the extended, CCI is collapse phase due to the counter ions, and then CCB phase which is due to the Crowder phase. So here the phase space is epsilon MC, here the charge density A by AC is the charge density on the chain backbone. So what is interesting to note here is for the Z equal to 1, that the counter ion valency 1, we see there are intermediate value of A by AC where there is no CCB phase, CE to CCB transition happening, right? So this kind of strip is kind of extended up to a very large epsilon MC. So why this is happening, that due to the steric effects, the number of the Crowder that can condense of the polyelectrolyte is kind of limited, and this we expect if this is the reason, then the smaller Crowder should should be able to form some collapse behavior at this regime, and which was indeed the case. If we make the Crowder size the half of the monomer size, we see that the chain is now showing the RG value in the collapse regime, and the chain is induced is indeed forming a collapse form. So now, what are the conclusions? So first is the attractive Crowder induced CG transition, with Crowder acting as a bridge between the distant, or the bridge of the glue between the distant monomer. And the interesting part is this soft interaction of the attractive Crowder can give rise to this CG transition at a very low density. So we have worked with a very low density, like 0.025 volume density, and in the way the CG transition happening due to depletion effect requires a very huge density. I mean, in the terms of 0.6 volume fraction or sometime. So it's really nice that this kind of CG transition can be achieved by introducing attractive Crowders in the system. And the critical transition point this CG transition shows is very strict function of monomer interactions and densities, and even Crowder interactions, right? And the charge polymer also shows the same CG transition, even though even in the presence of counter ions, Crowder are able to are able to get into the globule form, right? So what we going further, since we have seen that the Crowder size is also playing a huge role where in making this transition happen. So it's really important to study what are the effect of the attractive Crowders. People have studied the repulsive Crowders in depletion effect, and showed that the smaller the size of the crowder, better the depletion effect, or the depletion effect can be achieved at a lower density. So we want to see what are the effect of these attractive crowder on this CG transition. We got some preliminary results for that with the different crowder sizes. We got that there's some non-monotonic behavior with the crowder size. That means if we increase or decrease the crowder size, the transition becomes easier from E to CB for a weak intrapolymer attraction, and for high intrapolymer attraction, there is a monotonic kind of behavior with the sigma C. This work is still going on. We'll hope to publish it soon. Thank you.
Okay, so let us all thank Hitesh for talking about some very fundamental concepts in polymer physics. So we do have a time for a few questions.
Well, I was just wondering what is the scaling between RG and N in your CB phase? Is it still 1/3 or is it?
Yeah, so it's 1/3. So that's what we have also confirmed, that we plotted with the scaling, RG scaled with the n power 1/3, and we indeed see that this is the collapse regime, that the 1/3 is for different n, they are collapsing. I mean, they're indeed in the 1/3 regime.
Yeah. So I have a couple of questions. One is the monomer and the crowder, are they chemically same or different?
So right now, we have a bead spring model. We have taken a spherical particle as a monomer and the same spherical particle as a crowder particle. So chemically, they can be, different as well. So right now, we have just taken they have the interaction, LJ interaction between them. As in no chemical interaction or any other interaction. Just purely Lennard-Jones.
What about their sizes? Are they similar?
Yeah. So in the first, I showed the case neutral polymer, and the charge polymer monomer size is equal to the crowder size. We are now varying the crowder size in the one we have.
The second question was, so when you look at your simulations data, right? What is the data that shows you the evidence of bridging in your simulations?
So first, visualization, we visualize the data, like how each, and then we quantify the bridging as well.
Do you have any plot to show?
So I will show you the thing that how we quantify the bridging, and we see that there are indeed the bridging crowders. Here you can see. Yeah. So what we did was here I'll show. So we find how many crowders are there, NK we are calling them, which are in contact with K monomers simultaneously. And if for example, we take K equal to 6 or 5, for example. So how many crowders are there which are in contact with 5 monomers simultaneously? We are calling them as a bridging crowder, right? And through that, we quantify that these bridging crowders, and we again plot NBC, that is how many crowders are there which are in contact with at least 6 monomers simultaneously, and we see that there is very nice increment of this NBC with epsilon MC. From there also we made a phase diagram, and this looks like
the reason I asked this question is, see, classically when you talk of bridging, right, in polymer colloid system, you have a polymer adsorbed onto the surface of two particles, right? That's a bridging, right?
Yes.
Is it a similar bridging that you're talking about here?
Yes, it's so that's what. So single crowded particle is kind of attached with the two different monomer. Like monomer from a very distant regime.
Thanks.
Very interesting talk. I was interested in the electrostatic properties. So when you introduce the electrostatic interaction, what are the cutoff that you're using, or you're doing any case-based summation?
Yeah, case-based summation. Yeah.
And does it depend on the cutoff?
Cutoff. We have taken cutoff. I think 25 or 30.
Okay, but 25 sigma. Well, that is too large, or?
Yeah, as far as I remember, we have taken this much. I forgot. They're doing in the case space, yes.